This is the key for the second part of the exam, which involved equilibria and acids and bases. First question was to write the equilibrium constant expression for this reaction. Okay, and I think just about everyone got that one right. Second question would be to calculate Kc. Okay, so we need to rearrange this equation. And the change in the number of moles of gas is +2. There's 4 on the product side, 2 on the reactant side. Okay, so we raise this to the second power. We use the gas constant that's in liter atmospheres per mole Kelvin. Okay, and that's on your formula sheet. Right, so we come up with 1.29 times 10 to the 22nd. And there's no units. Okay, for number 3, the question is to calculate the partial pressure of NOBr in this mixture. Okay, so Kp is given, and it is equal to the partial pressure of NOBr squared divided by the partial pressure of bromine times the partial pressure of NO squared. Okay, so we substitute these values in here, and first I solve for the pressure of NOBr squared, and that was 0.158. And then if we take the square root of that, that's 0.397 atmospheres. Okay, number 4. Okay, our reactant is a solid, so we would omit the NH4HS from the equilibrium constant expression. And we would only include the products in this case. They're both gases. At a certain temperature, the value of Kc is 8.5 times 10 to the minus third. Reaction mixture containing solid NH4HS has ammonia and H2S concentrations both equal to 0.166. Okay, so we substitute those values into this expression, and we get 0.276. Okay, that should actually be 0.0276. And okay, that doesn't change the next part. The next part is, will more solid form or will more solid decompose as equilibrium is reached? Okay, well, since Q is greater than K, the reaction will shift toward the reactant side, which means more solid will form. Question number 5. We have a reaction vessel that initially contains only N2O4 gas. We set up our ice chart. We have no NO2 at the beginning. It increases by 2x. N2O4 decreases by x. Our equilibrium constant expression is NO2 squared, the concentration of NO2 squared, divided by N2O4. Okay, our numerator is squared, but we have to square both the 2 and the x. So that gives us 4x squared. Okay, rearranging this, we have the equation for a quadratic. Solving for x, we get two roots. We can discard the negative root. N204 is 0.05 minus x. Okay, so that would be 0.0116. And NO2 would be 2x, so that's 0.0768. Okay, this next one, I think just about everyone got this one right. Okay, this is similar to one we had earlier, but it's just going the other direction. Number 7 is involving applications of Le Chatelet's principle. Would the fraction of methanol, which is CH3OH, that's a product, would that increase if we raise the temperature? No, and the reason is it's an exothermic reaction. Okay, we know that because delta H is negative. Okay, so heat is a product. So if we add more heat, the reaction is going to shift in such a way as to consume that heat and go back to reactants. So that one would be no. If we increase the pressure, okay, that would be yes, because we have fewer moles on the products, fewer moles of gas on the product side. Adding a catalyst would have no effect. Okay, question number 8. Hydronium concentration of a solution at 298 Kelvin is 9.7 times 10 to the minus 9th. Okay, so to calculate the hydroxide, we would take Kw, which is 1 times 10 to the minus 14th, divided by our hydronium. And so that would be 1.0 times 10 to the minus 6th. Okay, the pH is minus the log of the hydronium, so that's 8.01. Okay, number 9, determine the hydronium percent dissociation and pH of a 0.1 molar benzoic acid solution. Okay, the Ka, the acid equilibrium constant, is given. Okay, so we set up our ice chart. Benzoic acid starts out at 0.1 molar. It decreases by X. The hydronium and benzoate both start out at 0, and they each increase by X. Okay, so our equilibrium constant expression is hydronium times benzoate divided by benzoic acid. Okay, these are both X, so in the numerator we have X squared. In the denominator we have 0.1 minus X. Okay, we can approximate in this case because our initial concentration is more than 1,000 times greater than our Ka. So this simplifies to X squared over 0.100. So solving for X, we get 0.0255. Okay, minus the log of that is 2.59. The percent dissociation is equal to X over 0.1, which is the original concentration times 100%. And so that would be X. X is right here, it's 0.00255. And then our initial concentration is 0.1. And so that's 2.55%. Okay, and then number 10 is a strong base calculation. Okay, so we have calcium hydroxide, and we worked a problem similar to this in class. Each calcium hydroxide is going to produce 2 hydroxides when it dissolves. And so the hydroxide concentration is actually going to be twice that of the calcium hydroxide initial concentration. Our hydronium is Kw divided by our hydroxide, and then the pH is minus the log of this, so that's 11.48. Okay, number 10, morphine is a weak base. Okay, so we start out, we have 0.150 molar. It has a pH of 10.5. So I've set up the ice chart here for you. 0.150 is the initial. It decreases by X. Okay, each one of the products increases by X. Okay, part A, what is the value of the POH? Okay, so we take 14 minus the pH. The pH is given in the problem as 10.5, so the pH is 3.5. Now to find the OH concentration, we would take 10 to the minus POH power. Okay, so that's 10 to the minus 3.5 power, which is 3.16 times 10 to the fourth. Okay, and that actually is our X. Okay, and it turns out that X here is actually much less than 0.150. Okay, so we substitute these values of X into this expression, and that gives us our Kb. All right, using the relation that Ka times Kb equals Kw, we can then solve for Ka. We take Kw divided by our Kb, and that gives us Ka. Okay, keep in mind that pHs and POH values are going to be small numbers. Okay, usually between 0 and 14. Okay, they're not going to be large exponential values, 10 to the 6th, or small exponential values, 10 to the minus 8th. Okay, they'll be small values, usually between about 0 and 14. Ka and Kb values are typically small numbers, okay, with negative exponents. Okay, the exceptions would be strong acids like sulfuric or hydrochloric. Okay, those would have very large Ka values. Okay, for number 12, okay, would these salts form solutions that are acidic, basic, or neutral? Rubidium iodide would form a neutral solution. Rubidium is in group 1 of the periodic table, along with sodium and potassium and so forth. And it's a neutral cation. Iodide is a neutral anion. Okay, since it's a conjugate base of a strong monoprotic acid. Okay, HI gives up all its protons. It doesn't want them back, so I minus is not basic. So they're both neutral, both cation and anion. For part B, ammonium NH4 plus is an acidic cation. Okay, it donates protons to form ammonia. Nitrate is a neutral anion. It's a conjugate base of a strong monoprotic acid, nitric acid, HNO3. Okay, so we have an acidic cation, neutral anion, so that will form an acidic solution. Kf. K is a group 1 cation, so it's neutral. F minus is a weak base, okay? HF is not one of the 6 strong acids, it's a weak acid. So we have a neutral cation and a basic anion, so that would form a basic solution. Aluminum chloride forms an acidic solution for a different reason. In this case, we have a small, very highly charged cation, Al3+. Okay, because of the high concentration of positive charge, okay, it's going to bind water molecules tightly, which will weaken OH bonds and make it acidic, make it easy to donate protons. Number 13, in the following equations, identify the Lewis acid and the Lewis base on the reactant side. Okay, some things to look for. A Lewis base is an electron pair donor. Okay, remember electrons are negative. Okay, so a Lewis base has to be either neutral or negative. Okay, if it's positive, that indicates a deficiency of electrons, so it's not going to be donating electrons. Okay, so zinc 2+ would be the Lewis acid. Okay, it would attract electrons because of the positive charge. Okay, if we were to draw the Lewis structure of ammonia, there is a lone pair of electrons on the nitrogen that could be used for donation. In the second question, okay, the clue that OH- is the Lewis base, is the negative charge. Also, oxygen has 3 lone pairs on it. This is called boric acid. And if we were to draw the Lewis structure of boric acid, boron is in group 3. And so this actually only has 6 valence electrons around the boron. It does not have an octet. When it forms the borate ion, then boron has a full octet. Okay, so this is the acid and this is the Lewis base.